Hi folks. In this lesson we're going to learn about what the mole is and how it is used in chemistry, why it's so useful. So first, what is the mole? A mole is 6.022 times 10 to the 23rd things, and that's over 602 sextillion items. You can see this is a huge number. This is why we use scientific notation to express it, because there are just so many zeros there you'd lose track. So when we use the quantity, the mole, it's like using the word dozen. 1 dozen means 12 things. 1 mole means 6.022 times 10 to the 23rd things. So it doesn't matter what you're counting. You can have a dozen donuts, you can have a dozen bagels, you can have a dozen eggs, you can have a dozen cookies, you can have a dozen elephants. It doesn't matter. It's the same thing with moles. But a mole is such a huge quantity, it is usually only sensible to use it for teeny tiny particles. This number, 6.022 times 10 to the 23rd, is called Avogadro's number. And as I said, it's useful for describing quantities of tiny particles like atoms or molecules. And I'm going to use this word particles to mean any kind of small particle like an atom or like a molecule. So the mole is useful because it's used as a conversion factor to convert between number of particles and moles. We're going to convert between particles and moles using dimensional analysis, and here is an example of the two conversion factors we'll use to do this. 1 mole is the same as 6.022 times 10 to the 23rd particles, or 6.022 times 10 to the 23rd particles is the same as 1 mole. Which version of the conversion factor you use depends on the problem. It depends on whether you're trying to get rid of particles and go to moles, or whether you're trying to get rid of moles and go to particles. So, we've learned dimensional analysis before, but it was a while ago. So let's review the steps we use for dimensional analysis. Step 1 is to identify the known and the unknown. What are you given in the problem? What are you trying to solve for? Next, you draw the dimensional lines, and those are the train tracks, or if you prefer to multiply fractions, you can write it out that way. Third, you insert your conversion factor, and you need to choose the right conversion factor so that units cancel out. So you want the old units to go on the bottom and the new units to go on the top. The known units to go on the bottom and the unknown units to go on the top. Double check to make sure you've done everything correctly. Check to make sure your units cancel correctly. Check to make sure your conversion factor makes sense. Sometimes people accidentally put the units next to the wrong number. For instance, they'll say 1 inch is the same as 12 feet. That's not true. 12 inches is the same as 1 foot. So just make sure that you're setting up your conversion factor in the correct way. And then step 5 is to do the math. So, how many molecules are in 2.50 moles of C12H22O11? Okay, the formula here doesn't even matter. We've got moles and we want to know how many molecules we have. It doesn't matter if we had donuts or eggs. 2.50 moles is a certain number of particles, and that's what we're going to convert to. So what is our known? Our known is that we're starting with 2.50 moles. This is our known. And our unknown is what we're trying to solve for, and that's the number of molecules. So that's what I'm going to write at the end of the problem. I've got my known and my unknown, and I've drawn my dimensional lines to make room for my conversion factors. And my conversion factors, I'm either going to want to convert from moles to molecules or from molecules to moles. Please, please, please don't get confused. Remember, this is the abbreviation for moles. It's not the same as molecules. Mole is not short for molecules. It's short for moles. We want to get rid of those mole units and convert to molecules. So I want my mole units to be down below so that they will cancel out. Those units are going to cancel out. And I'm going to convert to molecules. So 6.022 times 10 to the 23rd goes on top because that's the number that goes with molecules, and 1 mole goes on the bottom. Then I do my multiplication. I do the math. I'm going to do 2.5 times 6.022 times 10 to the 23rd divided by 1. And the answer we get is 1.51 times 10 to the 24th. Now, it's important to watch your sig figs. Generally speaking, your sig figs will match whatever sig figs you have for your given. Okay. Usually, the number of sig figs here is the limiting factor. When you are multiplying by scientific notation, my recommendation, if you don't know how to use scientific notation on your calculator, is to multiply together the coefficients. So you do 2.50 times 6.022 times 10 to the 23rd. And when you do that, you will get 15.1 times 10 to the 23rd. So I'm just multiplying the coefficients together, and then I'm keeping this as its own answer, or as its own part of the multiplication problem. And then this is not correct scientific notation. So this is where I need to convert it to scientific notation by making this coefficient smaller to make it a number between 1 and 10. Because I made the coefficient smaller, I need to make the exponent bigger. And that's why I convert to the 1.51 times 10 to the 24. Let's do another example. How many moles of gold do you have? How many moles? That's my unknown. If you have 1.00 times 10 to the 23rd atoms of gold, this is my known. So, step 1, I've identified my known and my unknown. So I'm going to write 1.00 times 10 to the 23rd atoms of gold, AU, and I'm trying to solve for moles of gold. So I'm going to write that at the end because that's what I'm trying to get to. It's one step to get from atoms to moles. So I'll get rid of atoms and convert to moles. And now I need to think about what number goes with what. 1 mole is that huge Avogadro's number of atoms. Atoms are a kind of particle. So 6.022 times 10 to the 23rd. Plugging this into my calculator. Again, if you don't know how to handle scientific notation on your calculator, my recommendation is that you don't. Students often do it incorrectly. But what you do is you divide the coefficients. And then you subtract the exponents. So 1.00 divided by 6.022 gives you 0.16606 times 10 to the 23 minus 23 is 0. So this is the answer that I have when I divide the coefficients and subtract the exponents. Now, this is not correct scientific notation, so I don't want to leave my answer like that. 10 to the 0 power, anything to the 0 power, equals 1. So I'm really just multiplying this times 1. If I wanted to write this in scientific notation, the value would be 1.66 times 10 to the negative 1. I need to move my decimal place to make the coefficient bigger. So in response, I have to make my exponent smaller. I move the decimal place one time, So I drop the exponent one time and I go from 0 to -1. This would be correct scientific notation for this answer, and it's an acceptable answer, but it's kind of unnecessary. Scientific notation is most helpful when the number is really large or really small, and this number is really just 0.166 moles of gold. So either one of these answers would be fine to give, but the scientific notation really isn't necessary when the number isn't gigantic or super small. Let's do another example. How many molecules, that's what I'm trying to find out, are in 0.0250 moles of oxygen gas? So this is my known, and that's what I start with. 0.0250 moles of oxygen gas, and I'm trying to convert that to molecules. I need my dimensional lines, and I need to insert my conversion factor. I have to get rid of my old units, moles go on the bottom, and convert to molecules, so molecules go up top. And then I need to think about what number to write where. 1 mole is the same as Avogadro's number worth of molecules, that gigantic number, 6.022 times 10 to the 23rd. And remember, my recommendation is to multiply the two coefficients together. And in this case, doing that gets me 0.15055. And just carry my scientific notation over, times 10 to the 23rd. Now, this is not correct scientific notation, and it has too many significant digits. So I need to rephrase this in correct scientific notation with the correct number of significant figures. My coefficient needs to be a number between 1 and 10, so I need to move the decimal point 1 time. Because I made this number bigger, I must make the exponent smaller. My final answer should have 1, 2, 3 sig figs. 1, 2, 3 sig figs. So my final answer is 1.51. That, because that number's a 5, I'm going to round up the previous digit. And I said I was going to reduce the exponent because I had increased this coefficient number. So 1.51 times 10 to the 22nd molecules of oxygen. Let's try one final example. How many moles of water do you have if you have 1.25 times 10 to the 24 molecules? How many moles? That's my unknown. If I have this many molecules, this is my known. So I start with my known. And I'm converting to my unknown, which is moles of water. And I need to insert a conversion factor that gets rid of the molecules and brings in moles for my final answer. It may seem unnecessary to write the formula for the substance here, but eventually we're going to do calculations that do convert between one substance and another, and it's best to get into good habits now so that we can keep track of what numbers belong to what specific compounds when we learn to do those more complicated problems. Okay, getting rid of molecules. This 1 mole is the same as 6.022 times 10 to the 23rd molecules. Again, thinking about how we handle scientific notation, I'm going to divide the coefficients and subtract the exponents. When I do 1.25 divided by 6.022, that gives me 0.20757. That's too many sig figs, but we'll round that off later. Times 10 to the 24 minus 23 is 1. This is incorrect scientific notation because this number is not between 1 and 10. I have to make this number bigger to make it a 2 point something, which would be between 1 and 10. Because I made this number bigger, I have to make this number smaller. So I'm going to have 2.0757 times 10 to the 0. As we've said before, anything to the 0 power is just 1. So I really don't need this scientific notation at all because I'm saying 2.0757 times 1 is just 2.0757. I do need to think about significant figures. My known value is 3 sig figs. I've got 4 sig figs down below, so this is my limiting sig fig value, and therefore I'm going to round off after 3 sig figs, so that's going to be 2.08 moles of H2O. One thing I do want to point out, if you have moles, you probably have a sensible number of moles, like a number where you don't really need scientific notation to express it. Moles are specifically designed to accommodate gigantic numbers of particles, whether they are atoms or whether they are molecules. If you are giving an answer that's in atoms or molecules, then you're going to have a gigantic number, generally speaking. You're going to have to use scientific notation to express that. So just check your answer at the end and make sure it makes sense. If your answer is in moles, you should have a number that probably doesn't really need scientific notation. But if you're giving your answer in molecules or atoms, then you probably do need to use scientific notation. I hope this helped.